Hello, Dr. Hua. This is Colton with Thursday Group Lab B, and we're here to talk about Lab 4, optimal beam collimation and testing of radius of curvature. So the first part of the lab is the setup. So like most of the labs before, we have a Heaney laser that's set up and straightened along the rail using previous lab techniques. Spatial filters aligned using back reflection and previous lab techniques. The lens was aligned using back reflections and up to the spatial filter. And what's really cool now is that we have collimated light coming out of our collimation lens. And so we're going to zoom up on those fringes and show you that the bars there are lined up on the shear plate. And I'm going to move it back and forth, and you can see them move back and forth. So that means we have a good collimated beam. The purpose of this lab is to go ahead and we're going to measure the focal length of this lens right here by measuring the deviation of these fringes from straight or collimated. And to demonstrate this, I'm going to put the lens in right now and show that the resulting fringe pattern is at 45-degree angle to the collimated. And now I'm going to hand it over to Alex, and he's going to show why and how we can measure the focal length of this using this technique.
Alright, I'm Alex Marty working with Colton Noble, and here we have a diagram of our blown up shear plate thing, and we have our two overlapping wave fronts, and I'm going to explain the different values we were supposed to find. So D is our fringe spacing. It's the distance between the max of one fringe and the max of another fringe. S is our shear distance. That's the distance between the two wave fronts. And we can find that by measuring from the edge of where the light is to the edge of where the fringes start. And then alpha is our angle between the fringes and the reference line on the shear plate that tells us whether we're collimated or not. So we can take our values. We found the shear distance to be 8 millimeters, the fringe spacing to be 3.5 millimeters, and our angle to be 45 millimeters. We plug them into this formula here, knowing that the wavelength of our laser is 632.8 nanometers, and we use that to find the radius of curvature of our beam that's coming out of the lens. And the radius of curvature actually represents how far from the lens it is until it comes to focus. And because we have collimated light coming in, we know that this distance is actually the focal length of the lens. And we calculated that to be about 62.5 meters, which is gigantic, but it fits because we know that the shear plate is super sensitive to converging and diverging beams, so the fact that it's barely converging means that we are able to detect it with the shear plate. If we had a focal length of like 200 millimeters or something, we would not even be able to come close to see. Hi, Alex again, and I'm going to explain what we did for part E, which was to test the radius of curvature of a curved mirror. So looking down at our setup, from here over, it's the same thing we had before. We have collimated light coming out. We've turned around our shear plate, so the beam input direction is actually this way. So our beam just passes through initially. We have a reference lens here, and right now it's bringing light to focus right on the surface of the mirror that we're testing, and the light reflects back, goes back through the reference lens, and we see, looking at the shear plate, that we have collimated light because it's parallel to the reference line. And then what we do for this part is we record the position of the mirror here on the table, and then as we slide the mirror away, looking at the shear plate, we keep going, and there's another point where we get collimated light coming back into the shear plate. And then we take down this position of the mirror, and the distance between those two positions gives us the radius of curvature of our mirror. And now we're going to go over to Colton at the board, and he's going to explain geometrically why that is.
So Alex just got done showing you how we did the experiment on the lab bench, and I'm going to explain why we did it this way. The problem with using a mirror to measure using a shear plate is that it does not work in transmission, it works in reflection. And so because of that, we need to create a reference point to measure the radius of curvature with respect to. We do that by using this reference lens. And the reference lens, and like Alex said earlier, the focal length doesn't matter. It just needs to bring the light to a point. And so we bring this light to a point which is called a cat's eye. Once the light's at a cat's eye, we now have a reference to measure the radius of curvature with respect to. By moving the mirror back to its radius of curvature position, we all know that because of geometrical optics, that the light return will be a collimated wave. And that collimated wave returns back through the lens and back to the shear plate to show straight fringes. Hi, it's me again. So what we did this time is we're testing the low power focal length mirror here. So it's a very long radius of curvature. And we want to demonstrate first that we have straight fringes. And so in order to test this, we wanted to measure the deviation that the long radius of curvature mirror adds to the fringes. So we're going to rotate the cube 180 degrees. And you'll now note that we can see the mirror surface. And we can take the angle and the S number off of this by measuring the shear distance and measuring the angle of these fringes. We can go back and calculate what the focal length of this mirror is. And you can kind of notice that if you see here, they're pretty rough looking fringes. And part of that's because the mirror is not a very high quality mirror.
Alright, so I'm just going to tell you guys the numbers we got here really quickly. We got our shear distance was 7 millimeters, our fringe spacing was 2.5 millimeters, and our alpha angle was 65 degrees. And we plugged that into the same equation that we used in part D with the low power lens. And we determined that the radius of curvature of the beam coming from the mirror, which is equal to the effective focal length of the mirror, was 30.50 meters. And that matched up with what our TA said was should be the focal length of the mirror. And for the last part of the lab, the competition, I was able to assemble and align it in 4 minutes and 40 seconds, and Colton was able to do it in 3 minutes and 30 seconds. So I think that means I get 10 bonus points and Colton gets 11, just so it's documented. See you guys.